This is another video in the series of videos on stereoisomerism, and this time we have a very interesting question. How many stereoisomers are possible for MABCDE, trigonal bipyramidal structure? So let's first think what trigonal bipyramidal geometry is like, and it's like this. You see, so you have a central atom and you have 5 different atoms attached to the central atom. And since the number is 5, there is no symmetric solution to it. You don't have a solution, a beautiful solution like tetrahedral or octahedral. You have a non-symmetric solution. You have 2 different kinds of shapes here, 2 different kinds of positions here. So these 2 positions, this and this one, they are called axial positions because they are exactly opposite to each other, right? Like the North Pole on Earth is exactly opposite to the South Pole, and these positions, they constitute a triangle. They none of the 2 are exactly opposite to each other. We take these 3 positions, so they constitute a triangle. You can imagine like Earth in this way, and then you can feel that these positions are on the equator. So that's why these positions are called equatorial. Will denoted by EQ, and these 2 positions are called axial, like North Pole or South Pole on Earth. So once you understand this geometry and you understand that it's not completely symmetric, there are axial positions and equatorial positions, then you are ready to dive into this question. How many stereoisomers for MABCDE? What do I mean by MABCDE? Is like your central atom is M, and you have these 5 different attachments A, B, C, D, E to the central atom in trigonal bipyramidal geometry, and you have to decide how many stereoisomers are possible. Let's get to it. So let's first start thinking like you have an infinite array of these random molecules, and you have to figure out how many different molecules are possible, and all of them are MABCDE kind, and they are in trigonal bipyramidal geometry. And the first step is like in all of these molecules you will have to identify the axial positions, the axial atoms. So in the first one you see that the blue and yellow are at axial. How do you identify that? So the axial atoms should be exactly opposite to each other. For example, here in this shape, can you identify pink and blue? And then similarly in all other molecules you can identify the axial atoms. And there are 2 atoms which are at the axial position, and you have these 5 different possible atoms, pink and blue and yellow and green and black. And if you take pairs out of these 5 things, you can have 10 pairs, right? Because 5C2 is equal to 10. So one can have 10 pairs of atoms possible at the axial positions, right? So if we understand that, then we can have 10 cases. So we can have 10 cases. Let me show you how 10, because we can count it in a way like suppose you take these 5 spheres and you start thinking about pairs. Let's first think of pairs with yellow. Then you can have these 4 pairs, yellow and pink, yellow and green, and yellow blue and yellow black. Then let's discard yellow and then think about pairs with pink. So notice as we have discarded the yellow, we won't have the yellow and pink again. So we have pink green and pink blue and pink black, and then we can discard the pink and we can think with green. So with green we have green blue and green black, and then we can discard the green and we have only 1 pair left, this one. So there are 10 pairs you can count, right? 1 2 3 4, 4 plus 3 plus 2 plus 1, that should be 10. And this is what the 5C2 does. It gives you this number very quickly. So number of ways of selecting two things out of five things, distinct things. Okay, so once we have understood that there are 10 possible pairs of atoms at the axial position, we should also understand this, that if you take any of these two cases, like when suppose when the yellow and pink are at axial position, you take a molecule where the yellow and pink are at the axial position, and you take a molecule from this case when the green and black are at the axial position, you will definitely get two non-superimposable molecules because your axial positions are different. You would never be able to superimpose them. They are non-superimposable. So why this is important? Because we have classified, we have a plan, and we have 10 cases in our plan, and all the cases are mutually exclusive. So we can count very freely. We won't be counting one molecule twice if we count like this. And of course we have this plan, and these cases, these 10 cases here, they are also mutually exhaustive because you don't have any other case remaining. So, and one more very interesting thing is, like, all the cases are logically equivalent numerically, like in terms of counting. The number of molecules which you will get in this case 1 will be the same as the number of molecules which you will get in case 2. Why? Because what is blue could have also been the pink, and what is green could have also been the black. So this is a very yeah, beautiful kind of a reasoning, and this is very intuitive. I think a lot of people understand it, and they don't have words to explain it. But I have a few words if you could figure that out. So yep, so let's proceed. So the point is, like, you can think about only one of these cases, and all the cases will be similar, and that's why you will get the reach to the answer only after understanding one of these cases. So let's put our attention to the first case when the yellow and the pink, they are at the axial position. You can have different molecules. You can have a molecule like this where the yellow and pink are at the axial position, or maybe the yellow is pointing down and the pink is pointing up, but that's not a big deal because we can turn the molecule in such a way that the yellow will be pointing up. What do we do? How do we do that? So we can imagine this axis going from the green and the central atom, and you have this axis, and you can turn it, rotate the molecule 180 degrees around this axis. And when you rotate 180 degree, let's say in this fashion, from up to down, the pink will come here and the yellow will go up. The green will remain here because it's on the axis, and the blue will come here and the black will go at the back, and you will get something like this, right? So now this thing has become this is, and now if we compare it from the first molecule, you have yellow up, and pink down, fine. But you can also superimpose one of the other atoms at the actual position. So suppose we go for the black one, and the black one is now not at the same position as in the molecule 1, so we can do that also. So what we have to do is, like, you have to imagine this axis, yeah, the axial position, the axial axis, the axis going from the yellow to the central to the pink, and then you can turn the molecule around to bring, like, how many degrees? I think 120 degrees, to bring this black here and the blue there and the green there, and what you get is this. And let's remove the intermediate figures and then compare. Oh, these two were superimposable. So we still have only one molecule in this case. But if you understand the argument, so when you will bring the yellow and the pink, yellow up and the pink down, then you can then you go for the black, and you bring the black in the front. then you can have two cases. This in this molecule, in this molecule, it got superimposed with the first one, but you can have the second case, which would be like this. When the green and the blue are not getting superimposed after the yellow, pink and black are superimposed, and these two molecules, they are not superimposable. No matter how you rotate one or the other molecule, they will not be superimposed. Because what more can you do? Maybe you can go for superimposing the yellow, pink and the blue. So you can try that, but then you will not have green and black superimposed. So these are two molecules in case 1, and these are the only two molecules in case 1 if you follow the logic. So two molecules possible in this case, and similarly you will have two molecules possible in all the 10 cases. That's why you will have 20 stereoisomers, and they would look like this. So the first pair we have had already, the yellow and the pink at the axial position, and you superimpose the black and you get these two situations. Then you have the other case when the yellow and the green is at the axial position. This is a new case, and you superimpose the black now and you get these two situations. Then you go for the next pair at the axial position, the yellow and the blue at the axial position and the black in the front, and then you get green pink or pink green. And then similarly you go for all the possible pairs, and in all of these cases you will have two possibilities. So you have 20 molecules possible here, these 20 molecules. There's one more thing which is interesting. Look at the first pair, and you can see that if you think this axis, and what you do is like rotate in this fashion, and you rotate, the yellow will still be there, the pink will still be there, and you rotate in such a way like only 60 degrees this time. So you will bring this this blue right here, and this black will be here in the front, and this green will go there. What happens then? You get a molecule like this, right? And let's remove this molecule and bring it here, and then you see they are in mirror image relationship to each other. If this is the mirror, these two are the mirror images of each other. So these two molecules are in complete mirror image relationship. That's why these two molecules, this pair of molecule, this is an enantiomeric pair of molecules. These two are enantiomers. Similarly, you can do with all the rest of the pairs, and you can have 10 pairs of enantiomers. So you have 20 possible stereoisomers, and you can say that 10 pairs of enantiomers also. There is no meso here. Thank you.